Hey everybody, welcome back to chemistry. So if I can blow up the slide. And it says, the heater used in a 4.42 meter by 3.56 meter by 3.05 meter dorm room uses the combustion of natural gas, which is primarily methane gas, to produce the heat required to increase the temperature of the air in the dorm room. Assuming that all of the energy produced in the reaction goes toward heating only the air in the dorm room, calculate the mass of the methane required to increase the temperature of the air by 5.18 degrees Celsius. Assume that the specific heat of air is 30 joules per Kelvin mole and that 1 mole of air occupies 22.4 liters at all temperatures. Enthalpies of formation values can be found in a table. Assume gaseous water is produced in the combustion of methane. So if I can reduce the slide. Okay. So this is kind of a tricky problem. So let me tell you how I sort of think about this problem. So the first thing I might try to do is understand what pieces of information that we have and where we're trying to go. And so one key piece of information we have is it looks like we have the dimensions of a dorm room. So let me write that down here. So it's going to be 4.42 meters by 3.56 meters by 3.05 meters. So we have the dimensions of a dorm room, and we have to figure out how many grams of natural gas, which is methane, are required to heat up this volume of the dorm room by a certain temperature, which I think is 5.18 degrees. So in the end here, we're going to do some steps here like this, several steps. But in the end, what we want are grams of natural gas. And so this is methane. So the formula for methane is CH4. Okay. So let's try to figure out what some of these steps may be. So here, again, we have dimensions of length times width times height. So you might remember that length times width times height is volume. So we have a meters times a meters times a meters. So we multiply these three numbers together, we'll get some number here, we'll work it out what it is, and it'll be in meters cubed. So that is actually a volume. Now, one of the things you'll probably notice in this problem is they tell you the number of moles of gas that can be found for a certain volume. So what you have to do is you have to get meters cubed here into the volume in liters. And then once you find the volume in liters, then what you can do is find the number of moles of gas that you have that will occupy this space in the dorm room. Okay, then it gets interesting. So we have moles of gas. And so what you can do if you're really careful is you are given a specific heat for the gas. And so you can take the moles of gas and you can figure out how many joules are required to heat this moles of gas if you're trying to heat it by a certain temperature change. So that's a little tricky. But again, in the end, you can take moles of gas to joules of gas. And so here, the sort of the key element here is the specific heat of the gas, which is 30.0 joules per Kelvin mole. And another critical piece of information you'll need to solve the problem is you'll need to know the temperature. And so right now it's 5.18 degrees Celsius. And so one thing you may already see is that we'll have to get this Celsius into a Kelvin. That's a little tricky, and I'll show you how to do that. Okay, so now that you're at the joules, you can get this into moles of methane. And the way you get this into moles of methane is you're going to have to use the enthalpy of formations of the reactants and products for the reaction involving methane, which is the combustion of methane, where you take methane, you react it with oxygen, and you produce carbon dioxide, water, and heat. And then once you get the moles of methane, you can get the grams of methane by using the molar mass of methane. So you can see there are a bunch of steps here. Okay, so what I'm going to do is I'm just going to go ahead and start solving the problem. So the very first thing I want to do here is I want to take the dimensions of this room of width, length, and height and multiply them together to get a volume meters cubed. And so I actually did that earlier. And so what I got when I did this earlier was I got 47.992 meters cubed. Okay, so we'll just keep all the significant figures. And so I'm going to write down here 47.992 meters cubed. Now, what we want to do is get this meters cubed into liters. And so how might you do that? So what I would do is take the meters cubed, get this into centimeters cubed, and then get this into milliliters, and then you can get it into liters. And so I'm going to write up a train of fractions here that do these conversions. So one thing you're going to have to do is get the meters cubed into centimeters cubed. And I'm kind of hoping you'll be able to do this on your own. But let me show you how to do it anyway. So you have 1 centimeter is equal to 1 times 10 to the negative 2 meters. Okay, so this conversion is not good enough. We need cubed. So we have to cube the left side and the right side. And so it's going to be cubing the number and then cubing the unit. And then on the right side, it's cubing the number and cubing the unit, like that. So here, the answer is going to be, or the equality is going to be 1 centimeters cubed is equal to 1 times 10 to the negative 6 meters cubed. Okay. And so here, I'm hoping you can sort of figure out what fraction to write here. And so what we want is the meters cubed to cancel out. So it's going to be 1 times 10 to the negative 6 meters cubed. And then over on the numerator 1 centimeters cubed. So that's pretty good so far. And so what we have is, you can see the meters cubed cancels out, and now we have an answer in centimeters cubed. Okay, so what do we do next? Okay, centimeters cubed to milliliters. That's pretty easy. You remember that for every 1 centimeters cubed, that is 1 milliliter. So we can write here in the numerator 1 milliliter over 1 centimeters cubed. Okay, and now the next step is to get this into liters. And so I'm hoping you recall that 1 milliliter is a thousandth of a liter. So how do we write that in? Well, it'll be 1 times 10 to the negative 3 liters over 1 milliliter. Okay, so now if we wanted to, what we can basically do now is figure out, well, if you have a room of these meter dimensions, you can figure out how many liters of volume that is. And so I actually did that earlier, and let me show you what I got. I got 4,792 liters, and we'll just keep all the significant figures. Okay, so the next step is I want to take that volume of air in liters, and I want to try to figure out how many moles that is. So you have a conversion that could be useful. You're told that 1 mole of air occupies 22.4 liters of space. So let me write that out. 1 mole is equal to 22.4 liters. And so you can write out 2 fractions. I'll just write 1, that may be useful. 1 mole over 22.4 liters. And so it looks like I want to use this fraction to get liters to cancel out to get an answer in moles. So it's going to be times 1 mole over 22.4 liters. And so if you work that out, I get, at this point, 2,142 moles. Okay. So far so good. We're now at moles of gas, and now it gets a little tricky. So we have to figure out, if we have this number of moles gas, and we're raising the temperature of the moles gas by 5.18 degrees Celsius, how many joules of energy is needed to do that? And so you're able to work out that by knowing the specific heat of the gas. And so let me talk a little bit about that. And so Here you have 2142 moles of gas. And so let me just write in the specific heat of the gas. And you see it's 30.0 joules over Kelvin moles. And so one thing I think you can see is that here the moles cancels out, which is really good. And so if you were to do the math here, it'd be 2142 times 30. You would get an answer in joules per Kelvin. But here's the problem. What you want to do is get an answer only in joules. And so we have to get rid of the Kelvin somehow. And so you will note in this problem that we have the temperature increase needs to be 5.18 degrees C. And so you might say, okay, I want to convert that to Kelvin. But you have to be very careful here. And the reason is this. If you take 5.18 degrees Celsius and then you were to sort of convert it to Kelvin like you normally do, then what you would do is you add 273.15 to get the temperature in Kelvin. And then if you were to use that temperature, you would get the wrong answer. So I need to talk about why it's the case. Here's the problem. You see this temperature here? This isn't so much an absolute temperature. This is actually a temperature change. So let me note here that this is not so much T, but delta T. It's a temperature change. And then let me point out something very important about the Celsius and Kelvin scales. And so let's say we have a thermometer here. This is in Celsius. And let's say we have another thermometer here in Kelvin. So one thing you probably know is that the freezing point of water is 0 degrees Celsius and the boiling point of water is 100 degrees Celsius. And you can convert that to Kelvin by just adding 273. So here in Kelvin, the freezing point of water is 273.15 degrees Kelvin, and then the boiling point of water is 373.15 Kelvin. Okay, so that's fine, but here's where it gets a little bit interesting, is that the temperature changes for Celsius and Kelvin are exactly the same. And the reason is, whatever case you're using, the Celsius scale or the Kelvin scale, that you have the same number of degrees between the freezing point of water and the boiling point of water. So whether it be Celsius or Kelvin, you have 100 degrees between them. So you have 100 degrees on this scale, and you also have 100 degrees on the Kelvin scale. And so what that means here is that the width of a degree in the Celsius scale here is exactly the same as a width of a degree on the Kelvin scale. And so here, if the temperature change is going to be 5.18 degrees Celsius, it's going to be exactly the same value in Kelvin. Again, this is because it's a temperature change. So it's going to be 5.18 Kelvin. Okay, so now we can go back to this problem here. We figured out the temperature change in Kelvin, so let me show you what you do here. You multiply here by 5.18 Kelvin. And so what you can see now is that the Kelvin cancels out, and then you'll get an answer in joules. So let me work that out. I'm going to erase this stuff here. So what you get now when you do the math is I get 332,944.5 joules. Okay, so now your final step is now you know the amount of energy needed to heat up this volume of air. You have to figure out how many grams of methane must be combusted to produce this amount of joules of energy. So I'm going to clean some stuff up here and change the slide, and then I'll talk about that. So I'll be with you in just a second. Okay, so this is the amount of joules that are required to warm up that volume of air. And so you have to figure out the grams of methane that are required to produce this joules. So what you have to do now is you need to know something about how methane combusts, and then you have to figure out, well, for every mole of methane, how many joules do you get? So first thing we're going to do is we're going to write out the combustion reaction for methane. So methane, which is natural gas for the most part, methane has the formula CH4, and this is in the gaseous state, and I probably have to indicate that here. and then it's going to react with oxygen in the air, and this is also in the gaseous state, and it's going to produce carbon dioxide in the gaseous state. And then the problem indicates that in this particular combustion reaction, we should assume that water is in the gaseous state. And so now it's probably a good idea if I balance the equation. So it looks like the carbons are balanced. And so what we have to do is balance oxygens. So I think I need to put a 2 there. So there are a total of 4 oxygens on the product side. And I need to put a 2 here. So there are 4 products on the reactant side. And so it looks like this is a balanced equation. Okay, so your goal now is to figure out how many joules of energy is released in this chemical reaction per mole of methane that reacts. So the way you figure that out is through a particular formula. What we're trying to find is the enthalpy change of this reaction, which is going to give you the heat in joules. And so I need to remind you a way to figure out the enthalpy change of the reaction. So one way you can find the enthalpy change of the reaction is what you can do is you can get the sum of the heats of the formations of the products. And so I'm going to write here N times delta H F of products minus the sum of the heats of formation of the reactants. So let me kind of remind you of something. So let's look over at here the heats of the formation of the products. And so you can look up the values of the heats of the formation of the products. And so there's a link there to a table. And I will get the values in just a moment. But this N here in this formula next to the products is just to remind you is that if you're calculating the heats of formation of this reaction, what you have to do is you have to multiply by the number of moles here. So here, if you look up the heat of formation of carbon dioxide, you only multiply by 1 because there's only 1 mole here. But with water, what you'll need is you'll need the heat of formation multiplied by 2. So at this point, what I want to do is I want to work out or find out what the heat of formations of each of these molecules is. And so I have that information here, so let me just kind of circle that here and write it down on the board. So what we need is heat of formations here, so I'm circling that. And then what you want to do is we want to get the heat of formation for methane in the gaseous state, and then heat of formation of carbon dioxide in the gaseous state, and of water in the gaseous state, and then oxygen also in the gaseous state. And so let me go ahead and just write those numbers down here. So for methane, I'll just write the numbers up here. It's negative 74.6. And the units here, you'll just have to remember, are kilojoules per mole. So I'll just write that there. Here, the heat of formation of oxygen is 0. I think I talked about how if you have an element in its natural state at room temperature, then the heat of formation is set to 0. So oxygen is a gas at room temperature, so its heat of formation is set to 0. So I'm going to put a 0 here. The heat of formation for carbon dioxide I have there, it's negative 393.5. And the heat of formation for a water is going to be negative 241.8. Okay, so from these heat of formations, let's find the enthalpy of the reaction here. So let me just do this here. Okay, so now we have to find the enthalpy change of this reaction. So let me go ahead and sum up the heat of formation of the products and then subtract from it the sum of the heat of formation from the reactants. And so for the products, and so I'm going to look at the products here. I have carbon dioxide, which is negative 393.5. And then we're going to add to it the water's heat of formation, but we have to multiply by 2. So it's 2 times negative 241.8. So those are the products, right? Let me just write that here, products. and then we're going to subtract from it the formation of the reactants. And so the reactants are negative 74.6 plus 0. So if you do the math carefully, what I get here is negative 802.5 kilojoules per mole. So this is the enthalpy change of the reaction, or you can think of it as how much heat is released in the reaction. That's acceptable too. Okay, so now we can finally take this joules of energy needed to heat the room and figure out how many grams of methane are required. So let me erase some things and I'll talk about how to do that. Okay, so our goal is to take this joules of energy and figure out the grams of methane required to produce this joules of energy. And so I think you can sort of see here that eventually we're going to need this value here of negative 802.5 kilojoules per mole to do this conversion. So first thing I want to do is get joules into kilojoules. So let me go ahead and do that. So it's going to be times 1 kilojoule over 1,000 joules. Okay, so we're good to go there. So you can see that at this point, the joules cancels out, and now we're at kilojoules. Okay, so next step is now we're in kilojoules. We can actually get this per mole, and it'll be per mole for the reaction. And you can see that the mole, the reaction, is where you burn up 1 mole of methane. So when we work out 802.5 kilojoules per mole, it's really per mole of methane. And so we can leave out the negative sign because in the end, if you have a mass in grams, you're not going to have a negative sign. So we can just leave out the negative sign. So let me go ahead and put this information here. So we want 1 mole over 802.5 kilojoules. And it'll be, again, 1 mole of methane. And so the very final step is all you have to do is convert moles of methane to grams of methane. So it's going to be like this. You'll have to work up the molar mass of methane. And then I think what I got earlier, 16.043 grams of methane over 1 mole of methane. Okay. So let's just cancel units and see if we get things in grams as we hope. So kilojoules cancels out, moles of methane cancels out, and so grams of methane carries into your answer. And so when I did this earlier and rounding to correct number of significant figures, I got 6.66 grams of methane. Yes, the devil's number of methane. Okay, so the answer is this. Thank you for listening to that. We'll see you next time.